I start thanking today's speaker, Alessandro Sozzetti, for accepting our invitation to hold this this joint seminar. I ask the courtesy to Katia Biazzo to introduce Alessandro, as she's much more familiar than me with the arguments of the talk. So, Katia.
Okay, good morning, everybody. It's a pleasure for me to introduce Alessandro Sozzetti. Alessandro studied and then got his master's degree at the University of Turin. Then he spent several years in the United States, in particular at the Space Telescope Science Institute at the University of Pittsburgh, where he got his PhD, and then at the Harvard-Smithsonian Center for Astrophysics. In 2009, he came back in Italy as a becoming researcher, and then in 2016 he became senior researcher. Alessandro is a great expert of detection and physical and orbital characterization of exoplanets and their host stars, mainly using optical and infrared facilities both from space and ground. He indeed has many rules of responsibilities and projects both from the ground, like HIRES, HARPS, ESPRESSO, HARPS, but also from the space, like Gaia, TESS, PLATO. And today, Alessandro will talk about high-resolution point of view of planetary systems demographics. And Alessandro.
Hey, thanks, Katia, and thanks again to the organizers for inviting me. It's really a pleasure to be able to be here today. I will try to bring you through, let's say, not at all exhaustive, but hopefully interesting review of some of the most intriguing findings in the exoplanetary field that are known to date, focusing in particular on some aspects of what we call exoplanet demographics. The demographics of exoplanets you see here represented, for example, in a mass orbital period diagram of the detected companions around stars approximately in the solar neighborhood. And you see represented here in the various boxes what are today the approximately known classes of planetary mass companions that have been identified through a variety of detection techniques. As you can see, it is pretty clear that after a couple of decades of searches, we are beginning to just marginally be sensitive to companions with a mass and orbital radius of Jupiter. And we are definitely not yet reaching the sensitivity to objects with the same orbital period and same mass as our own planet. Nevertheless, the successes of the most important planet detection methods, in particular radio velocity and transits, the focus on the former, on the detection of orbital motion dynamically identified through the wobble in radio velocity space of the central star, pushed and pulled by the orbiting companion, and the latter transits instead exploiting the geometrical effect of an eclipse of the planet, given the sufficiently good, essentially perfectly edge-on configuration of its orbit, such that the line of sight of the observer actually can see the eclipse. As I said, these two planet detection methods are the most effective and are the bulk of the and produce the bulk of the most important results known to date that allow us to investigate indeed the demographics of the planet sample. Demographics implies measuring, given a variety of planetary parameters, occurrence rates, that is, frequencies, trends and correlations among all the parameters that I am listing here. This is an approximate, not fully exhaustive, but reasonably complete list of the crucial parameters that we can determine for the discovered planetary companions. And the fundamental point to bring home is the fact that when we have a large sample of objects such as the ones described here in terms of parameterization, you can begin to study functional form of the number of planets and the number of orbiting companions as a function of the various parameters in play. Studying these distribution functions is fundamental because they are the key imprints of the processes at the heart of planet formation and evolution itself. Once you have a reasonable representation, more or less accurate of these distribution functions, you can compute the occurrence rates, which are simply the ratios between the number of detected planets to the number of stars around which you would have been able to detect, in fact, such planets. This seems easy an operation. It is not, in fact. We have to be careful because different survey programs with different techniques have different observational biases. We have seen some of these in the previous plot, where, for example, the transit method is particularly sensitive to identifying objects with very short orbital separations, while conversely, radio velocity work can detect companions out to several astronomical units, for example. And so different techniques and different survey programs, even with the same techniques, have different completeness levels and reliability levels that have to be estimated on a single program basis. This is not at all a trivial task, and it is, in fact, now an ongoing, very important chunk of work in the exoplanet field to account for these potential deficits and deficiencies and limitations of the survey programs when we are doing demographics calculations. I have listed here a very large number of parameters. It will not be possible to discuss in just half an hour or so all of them, all the correlations and trends and occurrence rates as a function of everything. So I'll cut short. I will not touch upon, for example, ages and binarity issues in connection to the host properties, and I will only very little and very briefly discuss effects related to orbital eccentricity and inclination. The most relevant results in terms of planetary systems demographics come from the transiting systems. These have been observed from space in particular, and they have provided a very large number of detections, especially thanks to the Kepler mission. The detected objects provide directly a measure, given the knowledge of the radius of the primary star, a measure of the size of the orbiting companion. And you can see on the upper side the distribution of planetary radii, and you see that it does have a very clear upward trend at increasingly smaller orbital sizes. The same is seen, for example, in historical radio velocity survey program results. This is the diagram on the bottom instead. Radio velocity programs measure an estimate of the mass of the companion, not entirely, not the true mass, only a projected mass, what we call the minimum mass, because the radio velocity techniques is intrinsically one-dimensional in its form, and provides only, as I said, a lower limit to the mass of the detected companion. Nevertheless, it is possible to study the mass function of the radio velocity detected companions, and you also indeed find an upward trend of increasingly occurrence rate of these companions, the smaller their masses. So when you see distribution function in mass and radius, you see very similar trends. These are usually understood in terms of power law fits. These are the simplest representations of these distribution functions, and they already provide very important insights on the way these planets might have formed. For orbiting planets that are seen in transit, you can combine the knowledge of the mass from radial velocity work and the radius from transit detections, and derive actually the parameter that allows to disentangle the true mass of the companion, because the sign of the inclination angle, which is entirely unknown in the radial velocity work, can be measured directly, because we know the inclination as soon as the planet is known to be transiting. With the mass and radius, we can enter this other fundamental diagram of exoplanetary demographics, which is the planet radius diagram. The mass-radius relationship, or relation, for transiting systems is a fundamental tool that we use to understand the properties of these objects, because given mass and radius, it is possible to measure a density, and given a density, it's possible to infer approximately the bulk composition of these objects. And you see here, for example, that very large radius and large mass companions are typically described as Jupiter and Saturn are, in terms of very volatile compositions, mostly hydrogen and helium, while the lower you go in mass and radius, you begin to have to call into question the possibility of these objects becoming more and more similar in terms of composition to our own Earth. Measuring the densities of small planets, the ones that you saw in the bottom left corner of the previous diagram that I showed, is a not at all easy task. If you can see here in this diagram, the distribution of planetary radii for objects that have a radius estimate from, for example, the bulk of detections from the Kepler missions, and the subset of those companions for which it was possible to measure the mass through radial velocity follow-up work, and therefore combine the two. As you see, the green distribution of objects with measured densities, because there is also a dynamical mass estimate provided by radial velocity work, is only a very small fraction of the actual bulk of objects with detected radius. It is difficult, but it's a key measurement to make, to be able to have a precise density for these small objects, because once you have the approximate identification of the bulk composition of these objects, it is also possible to make inferences on one key parameter, which is the atmospheric scale height, that tells you something about the ability or inability to potentially detect and characterize the atmosphere of a given companion. And a fundamental input for future projects that I will very briefly touch upon at the end of the talk, such as JWST, the James Webb Space Telescope that was just recently launched, or the Ariel M-class mission from the European Space Agency, will necessarily profit from very precise measurements of the densities of the small mass companions and small size companions. I will now discuss the contribution to exoplanet demographics through some key results of that we have obtained in the last 5 and 10 years, respectively, with 2 facilities from the ground that have been operational in the north and in the southern hemisphere: the HARPS-N high-resolution spectrograph and the ESPRESSO high-resolution spectrograph. The former is mounted at the Telescopio Nazionale Galileo in the Canary Islands, and the latter instead is mounted at the Very Large Telescope in the Chilean Atacama Desert. These two are spectacular tools for measuring dynamical masses, both of non-transiting and transiting companions. They have very high resolution, very high stability, and at visible wavelengths, they allow to measure HARPS-N radial velocity shifts with a typical precision of 1 meters per second, and ESPRESSO instead goes down almost by a factor of 10 in terms of precision, reaching the 10 centimeters per second level. There are 3 very large programs, 2 guaranteed time observation programs on HARPS-N and ESPRESSO, and another one, the Global Architectural Planetary System, running on HARPS-N now for almost a decade, gathering essentially the interest of the whole of the astronomical community interested in Italy in exoplanetary science, that have, as I list very briefly here, some key objectives at hand to be undertaken. And as I mentioned, these two instruments have been extremely successful in measuring dynamical masses of companions seen in transit by space missions such as Kepler and TESS. They have also been able to detect very small mass companions not transiting around nearby stars, and they have carried out programs to investigate the general architecture of planetary systems and the potential origin of their diversity as a function of a variety of stellar properties. Let's go back to the mass-radius relation, for example. You see here a very recent diagram we plotted in the mass-radius diagram, all objects with a mass, let's say, lower than 30 Earth masses and a radius below that of Neptune, which is approximately 4 Earth radii. All these objects have received a mass measurement to better, let's say, than 30%. So we know the masses with 3 sigma as precision or better. They are a key sample to check the potential composition that you see, for example, the representation in the lower point of the lowest value of radii between 1 and 1.5, all aligning along a line of composition that is essentially the same as the one that describes the Earth and Venus. All these objects have a composition that is similar to that of the Earth. They have radii that are definitely larger than that of the Earth. They have masses that are definitely larger than that of the Earth. These are called super-Earths. And this sample, with very well measured properties, is ever increasing. And it has fundamentally been contributed in terms of number of detections by the HARPS-N spectrograph and in particular, the GTO program running now for more than 9 years on the instrument. This is really a spectacular contribution obtained by the group and the instrument. Other intriguing features that can be seen in this lot of objects detected, for example, a potential dirt lack of objects that you can see by comparison with these two diagrams in the sub-Neptune type regimes. These are companions with radii between 2 and 4 Earth radii. They have a large coverage of the available parameter space of masses and radii if you confine them to the ones orbiting cooler stars than the Sun, with effective temperature below 5700 Kelvin or so. If you look at the same sample orbiting hotter stars, you see a clear lack of companions that are simply not detected, they are simply not seen, in a regime of orbital radii, planetary radii between 3 and 4, approximately, and with masses of order of 7, 8, 10 Earth masses and larger. This is a very interesting result because the lack of these companions that should have been rather easy to detect, in fact. The larger the size of the object in transit and the larger its mass, the easier it is to detect it with with both the detection methods I outlined. But the fact that they are not seen around the hotter stars tells you something about the fact that the mechanisms at play for forming planets around stars of different spectral types are not exactly operating in the same way. A very intriguing feature that was uncovered, that is another key tool for understanding planetary demographics today, is the non-monotonic behavior or bimodal behavior of the radius distribution for small size companions. You may have seen a hint of the fact that the radius distribution was not just piling up at increasingly higher and higher frequency, the smaller the radius of the object in the previous slide. But here, recent results have actually pointed out the fact that there is a clear dip in the occurrence rate as a function of orbital radius, of planetary radius, at approximately 1.5 to 2 Earth radii. There are two peaks at approximately 1.3 and 2 and 2.3, 2.4 Earth radii, plus a dip, a valley. The so-called radius valley is understood as a fundamental imprint of processes that are most likely connected to effects of photoevaporation of these companions that are very close in. I remind you again that planetary systems seen in transit are most likely found very close in, and so they are very strongly radiated. And these different pileups of planetary systems with smaller radii at a little bit closer in and larger radii a little further out, or expressed in terms of flux to the planet, hotter planets with higher incident flux with smaller radii, and larger planets with lower incident flux at larger orbital radii and larger planetary radii are two outcomes of photoevaporation processes. That's the way we understand today the evidence for this distribution. Once again, the fundamental contribution from the HARPS-N instrument has been to measure the densities of exactly these two populations for a very large number of the detected companions, for approximately 50%. And this is a sample of the various characteristics that come in various flavors, cover a large number in terms of decades of orbital periods, and cover an interval of rather high relevance in terms of planetary density, with the very low density objects seen further out, and the most high density ones always identified very close in. There are some other very interesting features in the Kepler sample of detected transiting companions that allow, for example, to study the statistics or their frequency as a function of planetary or stellar mass. There are two ways of seeing the problem. One study can be done measuring the occurrence rate of these companions as a function of planetary, as a function of stellar mass or stellar effective temperature. One can also see the number of planets that are identified as a function of stars of given spectral type. These two ways of representing the dependence of this parameter as a function of stellar property return clear evidence of the fact that increasingly higher mass stars tend to host increasingly lower amounts of planets. There are other very key, important key features in the orbital parameter and orbital and planetary frequency distributions that are connected to stellar properties. The planet-star connection is seen, for example, for giant planets as an increasing function of stellar mass and stellar metallicity. Chemical composition of a given star is also a fundamental parameter that drives the likelihood of a given star to host a planet or not. These relationships with increasing frequency as a function of stellar mass or stellar metallicity are very well established for giant planets. A little bit less so for smaller mass companions, where these trends are better understood. Other interesting trends that can be seen in the sample, if we keep ourselves in the giant planetary mass regime, are, for example, clear trends of increasing frequency with orbital radius or orbital period, if you like. This is not a monotonic function, and there seems to be evidence for a break in the frequency, in the occurrence rate, and an approximately orbital separation of maybe 3 to 4 astronomical units. After which there seems to be a decline in the frequency of such companions. This, if you look at some results of some surveys. other results of other surveys tell you apparently a different story. The increase in frequency as a function of orbital radius that occurs does not necessarily stop at the 3 to 4 astronomical units orbital radius range. And this is one classic example of what I said at the beginning, the fact that different surveys, even with the same technique, have different biases, they have different completeness limits, they have different levels of sensitivity, and this can sometimes result in potentially discrepant results, such as the ones that I showed you. We are being able to begin to tell something interesting along the story with the HARPS-N results. This is a calculation that is ongoing. It will be the matter of a publication soon to be submitted, in which we are redetermining the occurrence rate of giant planets at relatively large orbital separations, maybe up to several astronomical units, 5 to 10 astronomical units. And for a specific sample in which we already knew of the existence of close-in small mass and small size objects already identified through previous studies. The outcome of this investigation is telling us something that is going a little bit more along the line of the former, the latter study that I showed you before, in the sense that the occurrence rate doesn't seem to decline very quickly as a function of increasing orbital periods, for orbital periods extending after a couple of thousands of days. Another important contribution that comes from the HARPS-N spectrograph and again the GAPS program that I mentioned before focuses on the statistics of detections of small mass companions, non-transiting, around a well-defined sample of early M dwarfs. These are low mass stars within a narrow interval of stellar masses between, let's say, 40 and 60% of the mass of our sun, and around these we have actually measured, determined, detected more than a dozen companions. Some have been announced, some are being studied further, and are in the making for being published. This recent study that has just come out in the literature just barely a week ago has addressed the general sensitivity of our survey, and has allowed us to study the frequency of these companions as a function of their properties, in particular orbital separation and detected mass. And you see in the two diagrams on the right the fact that, for example, we reassess a clear increase in planetary frequency for the lowest mass companions that we detected, which are much more frequent than the larger guys with 10 Earth masses or so. And in particular, we also clearly detect an increase in planetary frequency at longer orbital radius. One other very intriguing aspect of planetary demographics is planetary multiplicity. Planetary systems often come in multiplicity larger than 1. The variety of orbital configurations that you see, for example, sampled briefly in the left diagram, tells you something about the extreme diversity of these objects. There are very different orbital arrangements, and they come in all sorts of configurations and architectures. Recent studies, based again on the Kepler mission results, have allowed to study the multiplicity rate of stars known to host a planet, and it looks like objects with systems with as many as 4 planets are more or less as likely to be found as the ones that are hosting only 1 companion, while very, very high multiplicity systems, such as those with 5 or 6, we have 8, by the way, are increasingly less common. To date, we still have to find a real true solar system analog in terms of orbital architecture. Studies of multiplanetary system demographics have also allowed to, always based on the Kepler mission results, have allowed for example, to establish the fact that eccentricities of these companions appear to be extremely low as soon as the multiplicity is higher than 1. This is the diagram on the right that you see. Objects in the Kepler field identified by Kepler mission that appear single typically have a little bit higher eccentricity than the one in multiple systems. Conversely, not only you can study the trend of eccentricity as a function of planetary multiplicity, you can also study how well aligned these objects are. When they are multiply transiting systems, they all have to have approximately the same orbital inclination with respect to the line of sight of the observer. And the tightness of the smaller the difference in orbital inclination, the larger the number of planets you can actually catch in transit. And in fact, you also see trends of decreasing orbital inclination of a given number of all the number of detected companions as a function of increasing multiplicity of the companions. These are also extremely informative results that must be fed into planet formation evolution processes. In particular, these orbital architectures and the eccentricity and inclination of these companions are key insights in understanding dynamical interactions between high multiplicity systems. The last interesting results that was identified very recently in multiple systems is the fact that if you take a look at the sample in the left, you may even by eye tell that multiple objects, especially the ones with very high multiplicity rate, 3, 4, 5 companions, appear to be more or less similarly spaced between one and the other, and they have similar sizes. And indeed, if you do statistics analysis of these companions, you actually find that the spacing in multiple systems in the Kepler field is indeed very similar, and the sizes typically do not vary much at all. This is the so-called peas in a pod effect that has also provided fundamental input on for theoretical studies that try to address the origin of these companions. One spectacular system that was detected by the ESPRESSO GTO program and had all the masses measured and determined is this one, TOI-178. It is a multiple system composed of 6 companions, all seen in transit by the TESS mission of the Kepler mission. And the ESPRESSO spectrograph allowed the careful determination of the amplitudes of the radial velocities and therefore the measurement of the dynamical masses for all the companions. This is extremely important result because these companions are extremely tight in a very strongly dynamically interacting chain of resonances. You see here the period ratios of all the companions that I have listed above, and a measurement of very high precision of their densities, such as the one that has been made possible by ESPRESSO, constitutes a fundamental ingredient for understanding the global origin of this system. Some objects are very aligned in multiple systems, some objects are extremely misaligned in multiple systems. This is a very interesting result that was obtained thanks again to ESPRESSO data, this time combining not only with transit photometry of the TESS mission, but also thanks to global astrometric measurements coming from the Gaia and Hipparcos astrometry missions. I will not go into the details of the combination of these techniques. Suffice it to say that it was possible, combining ESPRESSO and the Gaia Hipparcos measurements of global astrometry, to detect a very strong misalignment between the outer companion in this system. This is the system of Pi Mensae. The outer companion is very massive. It has a mass at the limit at the boundary between the so-called planetary and brown dwarf mass regime, which is on the order of 13 Jupiter masses or so. The companion detected by both astrometry and ESPRESSO data has a very eccentric long period orbit. there is a very small mass companion, a super-Earth, detected in transit by the TESS mission, that by definition has an inclination angle approximately 90 degrees because it is seen in transit. The inferred inclination of the orbit of the outer companion by the combination of Gaia, Hipparcos astrometry, and ESPRESSO other velocities is at least on the order of 50 to 60 degrees off. So the relative inclination between the two objects is not different by just 1 degree, like in the case of multiple transition systems, is very, very different. And the dynamical evolution of the system that has produced this architecture is a matter of ongoing studies because it is very, very, very interesting. Looking at similar sizes rather than similar spacings, you still get very interesting and potentially very surprising results. This is a case of the Kepler-107 system that was recently studied and had the two components, Kepler-107c and Kepler-107b, with dynamical mass measurements from HARPS-N. The analysis of these two objects brings in the mass radius diagram, they are indicated here, the knowledge of essentially identical, entirely indistinguishable radii and completely different masses that make for completely different densities of these two companions. So these objects are exactly the same size, but the masses are so different that the densities are completely different by a factor of 3. This is a multiple system, one of the typical Kepler ones, where the spacings, however, between the two objects is very small. How is it possible that two objects that are essentially the same size and very similar spacing, very close in spacing, have such different densities? It can only be understood whether if we assume that the one with a larger mass and therefore higher density has essentially undergone a huge collision with an object that possibly could have been similar in size, that essentially stripped entirely its more volatile materials and left the object essentially in iron core. This is a very interesting result that was obtained thanks to the HARPS-N data. I will probably skip this one because time is beginning to run short. Let's go to the summary of the open questions of the demographics field. I list here some that are, to my mind, the most relevant ones. We still have to figure out whether we are, as a solar system architecture, rare, typical, common, or not. We have not yet identified a real, true solar system-like configuration. And so this is an entirely open question in the field. We have to find objects that are increasingly similar in size and mass to the Earth at orbital distances from solar-type stars that are increasingly closer to the one we orbit at. And there are also other fundamental points to be addressed, such as the exact shape of the mass function, how does it depend on orbital distance and planetary and stellar mass and stellar properties in general. There are people who think that it is not mass, but the mass ratio, the most fundamental quantity that should be studied. And in general, we still have not at all exhausted our understanding of the variety of possible orbital architectures and the diversity of the physical properties of the planetary systems we continue to identify. All these have to be addressed in the future with new data, keeping in mind that the more the data come in, the more complex becomes the task of accounting for completeness and reliability in different survey programs with different techniques, such that all the results that one can publish in terms of particular measurements of occurrence rates are really reliable. So the future is bright in exoplanetary demographics. There is a host of missions that not only are already ongoing and will continue to produce data from space, but there are other ones that I'm listing here, upcoming, about to operate, or thought to as potential projects for the coming decades that really will try to address all the above questions that we have discussed. And very significant efforts will continue to be made from the ground, in particular with the very, very large telescopes and the extremely large telescopes that will come online in the coming decade. Ultimately, we will have to get the most global picture possible. The biggest contribution, the sooner to come, will be the one from the Gaia mission. Gaia absolute astrometry is expected to deliver spectacular results in the exoplanetary field. Don't worry too much about the complexity of this planetary mass semi-major axis detection diagram. Focus on the proper curves, the ones that correspond to the Gaia sensitivity to given mass and given orbital separation of a companion. The two solid and dashed lines above, the higher ones, are for a 5-year mission. Gaia has already moved beyond the 5-year nominal lifetime, and it is likely that it will be able to complete a full doubling of the mission lifetime, reaching a 10 years operation. The lower curves tell you the sensitivity of Gaia in case we actually do reach 10 years of mission. The bottom line is that whatever is detected is going to be in the approximately ballpark mass interval of giant planetary companions with many tens, hundreds of Earth masses, and typically at orbital distances of the order of 1 astronomical units or larger, up to maybe 5 or 10. We will not be at all sensitive to companions that are similar in mass to the Earth, but the fundamental contribution from Gaia will be the fact that Gaia is expected to be sensitive to such companions around an extremely large sample of stars, maybe 1 million, maybe more. Therefore, the number of expected detections is extremely large. We have a history that I'm providing here and summarizing of studies that have produced expectations for Gaia to be able to find several thousands, maybe 10,000, maybe larger, maybe more than 10,000 new planetary companions in the giant planetary regime. This is a key contribution that may actually even triple if we finally reach the 10-year mission timeline. That will allow the Gaia astrometry results on planet detections to populate all the distribution functions that we have seen before, and will allow us to study the fine structure of these distributions and the trends and correlations that we have touched upon. It is almost coming. In June 13th, we will have data release 3, and this will be the first Gaia data release in which we will be able to see results with orbital solutions for our stellar binaries and also substellar companions and planets. And here I show the only thing that I can show, that I am allowed to show because it's public. This is a Gaia image of the week that was recently published a couple of months ago, end of January. That shows the astrometric orbit of one of the known radar velocity planets. The star is HD 81040. The companion has a detected orbit of something like 400 microarcseconds in size. There's an orbital period of almost 900 days, so about 3 years, so just short of 3 years. And the Gaia results allow to pinpoint the actual mass of the companion because Gaia astrometry allows to measure the full orbital architecture, and so all the orbital elements are accessible by astrometry instead of the more limited knowledge coming from radial velocity. This is the very first result, and these are actually the only data points that you will see most likely of Gaia data until the next data release. For the Gaia data release 3, we will only be able to publish the solutions, but the data themselves, such as the ones that I show you here, will not be available to the community. To conclude, the ultimate frontier that we have to eventually to reach is the detection of analogs. This is the most daunting task, because the ones that we would really like to characterize, to find, and eventually to study in depth are the ones for which we could be able to get images. These are the ones that are orbiting not necessarily in transit configurations, but it can be separated in terms of the reflected light emission from the glare of the central star. For these, you need very high contrast imaging devices, even at short orbital separations. Particularly short orbital separation, sorry, and you need very, very large instruments on extremely large telescopes from the ground, or you have to go to space with the next generation of space missions. Nothing is capable of doing reaching the goal for the time being. The contrast and separation limits that you see in this diagram are extremely difficult to achieve, and precisely because this will be such a difficult process to do, it would be key to be able to have the targets at which to point at well ahead of time, rather than preparing such expensive projects and having to search with these instruments and space missions, not knowing whether we have planets of this type around a given star. We already know that they should be there. There is a plethora of estimates of the occurrence rate of Earth twins. I remind you, objects with the same properties of the Earth at the same orbital radius around stars, essentially with the same property as our Sun. This is a number that has floated as a function of time, you see here in the last decade, between very small numbers to extremely large numbers. The approximate consensus that is being reached these days is that probably 1 star in 3, 1 star in 2, 1 star in 2.5 may host an Earth-like planet. So this is a potentially very large number. However, it is an entire extrapolation. We don't have yet any actual detection on which to found our analysis. So these are always numbers that are produced based on extrapolations of known frequencies at different regions of the parameter space. So we have to actually begin to reach the point in which we'll be able to detect such companions. This is not easy to do. The path forward is provided primarily by extreme precision radial velocity instruments that are beginning to come online now and that will continue coming online in the future. And I will briefly touch upon the one classic result from the ESPRESSO instrument concerning our nearest neighbor, Proxima Centauri. Proxima Centauri is known to host a planetary system. It was first found to host a temperate Earth-mass planet with an orbital period of 11 days. Proxima Centauri is a very low luminosity star. It has only something like 20% of the mass of the Sun. And so the regime of, let's say, temperate regions where we would have on the surface the same temperature as we have on Earth, given same atmosphere is and composition of the companion is very close in. As I said, the orbital radius is just a small fraction of an astronomical unit. So Proxima B, sorry, there is a typo, it should have been B, not D, orbits in the habitable zone, as it is called, of Proxima. It was identified more than 5 years ago. ESPRESSO remeasured its orbit very accurately. You see the radial velocity curve on the right. This is the first panel on the left of the two right. And it also detected an additional closer-in companion with an orbital period of only 5 days and an amplitude in the radial velocity of only 40 centimeters per second. This corresponds to a companion with just 30% of the mass of the Earth. This is today one of the record holders in terms of smallest amplitude of the radial velocity signal, as smallest mass ever detected. And it tells you the prospects for identifying increasingly higher mass companions around increasingly higher mass stars that are ahead of us. Proxima B and D have a C in the middle. There is a third companion that is yet to be confirmed by ESPRESSO data, but we will continue collecting data and see if we actually find confirmation of this. This was detected with other data, in particular HARPS data, equivalent spectrograph working always in the Atacama Desert in Chile, that detected a companion much further out. This is a very cold object with an orbital period of almost 2,000 days. Always a very small, very low amplitude signal of just above a meter per second, and approximately a mass in the super-Earth regime. This is a very long orbital period, and the ESPRESSO data are still yet to be gathered in order to be able to confirm its existence. But it tells you something about the architecture, multiplicity rate, of just a planetary system very next door, and the potential of extreme precision radial velocities in addressing this, the goal of reaching the limits in terms of amplitudes down to the 10 centimeters per second level that are required in order to be able to address the task of finding these companions around stars like the Sun. And I think I can stop here.